Gravity is the force that pulls people and objects toward the Earth's surface. Without gravity, sitting in a chair or walking downstairs would be difficult. For example, when you drop a ball at any point on Earth, it will always fall straight down. That is gravity at work, pulling the ball towards the Earth's surface. But there is a difference between dropping and throwing a ball. When a ball is thrown, it still falls to Earth, but lands at a point further away from where it was thrown. If a ball could be thrown with enough forward velocity, it would fall around the Earth, creating a low Earth orbit. Like the ball, the space shuttle is actually in a continuous fall around the Earth. Astronauts and objects inside the shuttle are falling at exactly the same rate as the shuttle, thus creating the effects of weightlessness. Imagine an astronaut in an elevator on Earth. The elevator is going to the top of a very tall building. Suddenly, when he reaches the top, the cable breaks. The elevator begins to fall. Inside the car, the astronaut begins to float. He is weightless. If he had an apple, it would float too. That is because the car, the astronaut, and the apple are falling at the same rate of speed. You may have experienced moments on Earth when the effects of gravity seem to disappear, such as when you bounce on a trampoline or crest the hill on a roller coaster. Scientists can take advantage of a reduced gravity environment to isolate the effects gravity has on physical, chemical, and biological processes. A better understanding of these processes can be achieved by studying phenomena usually obscured by the effects of gravity. On Earth, scientists utilize specialized facilities such as drop towers and aircraft in parabolic dive sequences to test experiments for a few seconds at a time in an environment which is approximately 1/100th of the Earth's normal gravity level. However, many experiments require even smaller gravity levels and longer durations of free fall that cannot be achieved in these Earth-based facilities. In the constant microgravity environment of low Earth orbit, researchers have found that experiments in biotechnology, fluid dynamics, and materials science have produced dramatically different results than ground-based research. One example of this can be seen by examining crystals grown in a microgravity environment. These crystals contain fewer flaws and imperfections than crystals grown on Earth. The result: higher quality crystals for potential applications on Earth. However, even in the microgravity environment aboard the shuttle, there are other forces that may affect the results of experiments. Disturbances and vibrations caused by thruster firings, crew movements, and equipment operation can mimic the effects of gravity on experiment results. Disturbances that are significant for sensitive experiments. Disturbances that may negatively affect the results of those experiments. A simple demonstration illustrates how an outside force can affect the results of an experiment. The slightest disturbance to just one domino will cause the others to fall. Or try this experiment in your kitchen. The surface tension of a glass of water will support common paper clips. When the glass is bumped, the paper clips sink to the bottom of the glass. In order to understand the final data from an experiment conducted in microgravity, these disturbances and other parameters such as temperature and pressure need to be measured. Researchers may then use the data to determine if unexpected results were caused naturally or by these measured outside factors. At NASA's Lewis Research Center in Cleveland, Ohio, scientists and engineers have developed the Space Acceleration Measurement System, or SAMS, to measure and record vibrations and disturbances that may alter experiment results. SAMS is designed to measure, characterize, and record low-gravity disturbances on board the space shuttle. A single SAMS unit can monitor 3 experiments directly, as well as other experiments in close proximity. The SAMS hardware consists of a main signal processing unit and 3 remote triaxial sensor heads. The 3 sensors on each of these heads detect the different disturbances and their levels. The data is sent through cables and stored on disks, similar to the compact disks that are found in homes today. The sensor heads are mounted on or near an experiment, permitting disturbances affecting that experiment to be sampled. SAMS has the ability to collect data up to 20 feet away from the main unit. This enhances its versatility and allows it to serve a wide variety of microgravity science and technology experiments. SAMS is scheduled to fly as part of the 2nd United States Microgravity Payload Mission, USMP-2, aboard the Space Shuttle Columbia in March of 1994. During this mission, scientists in the Payload Operations Control Center, or POC, will be able to monitor some of the data that the SAMS unit is collecting in real time as the disturbances are occurring. Scientists can use this information to determine if adjustments need to be made to their experiments to avoid any unacceptable conditions. SAMS will support 4 materials science experiments on the USMP-2 mission. 3 of these experiments were developed or are managed by the NASA Lewis Research Center. The data that SAMS will collect for these experiments could lead to many advancements in processed materials, such as improved industrial casting methods, the development of superconductors, and the ability to produce higher quality crystals for use in commercial, military, and consumer electronic equipment.